All right, well, welcome back, everybody. This is lecture 5. I know last time we did a lot of conversation. Everybody did their presentations of the class of their projects, which I thought went well. I was very pleased to see what people were coming up with. I would encourage people to try to make an appointment with me, a virtual appointment with me this week to talk about their projects, because I think the hard part of these projects is to narrow them down and come up with something that's realizable. And especially in the context of creating a distributable application, the science in the application is a substantial part of it, but is not necessarily the most difficult or time demanding thing. And therefore, it really is important to start thinking about how not only what the science of the project is, but how you're going to turn it into something that can be distributed. I need to remind you, as usual, that this class is being live streamed and recorded and made available on YouTube. So today, I don't know how far we'll get. I want to start by going over some of the homework. I think we're caught up with all of the homework at this point in terms of grading. I hope so. I appreciate your patience with that. I'd like to go over a couple of the problems in the homework that raise some issues that probably need to be are worth reviewing. And though some of those issues came up in the first two homeworks, and then some of them were in the most recent homework that's due today. And then I would like to continue doing a little bit of modeling. And I hope we can talk about Michaelis-Menten rate laws and where they come from. And then talking about the Hill equation, and ideally beginning to think about how to apply the Hill equation to do network modeling, although I guess that it's not obvious that we'll get as far as that. And another thing that I'd like to talk about, whether it's this week or next week, will be thinking about questions for models. And that homework problem this week was trying to get people to think about these. I think that the technical sides of the mathematics of mathematical biology and the computing side of mathematical biology are both things that we can address fairly easily. And in some ways, they're taught in many places. The practice of modeling things, as I mentioned, can seem rather abstract, but there are issues that come up again and again when you're trying to define problems and solve them. And I think it's worth spending some time talking about those issues. So to begin with, I would like to come back to homework problem 3.1 and something that we spent a lot of time on 2 weeks ago, and that may have seemed rather mechanical, which was how to deal with stoichiometry. And it is mechanical, but it's also an easy place to make mistakes. And so the first homework problem was, I showed a diagram, this comes from Herbert's textbook, where the arrows indicate a multiplicity of chemical reactions. And the assignment was to write the rate laws on each arrow. And then it may have been not as clear, but I hope that people would then write the ordinary differential equations associated with A, B, C, and D for these. And when you have stoichiometry getting into coefficients for rates, it can be a little bit confusing. It's easy to make arithmetic error. And I thought it would be worth going over again how to do this together, so that we could make sure that everybody remembers how to do it. When you're doing gene regulatory and signaling networks a little bit, you don't wind up dealing with stoichiometry so much. When you're dealing with chemical reactions and metabolic networks, you deal with stoichiometry a lot. And so it's a good idea to at least remember what the rules are. And one thing doing this here in the classroom is that I don't have a drawing tablet. So it makes it a little bit more challenging to me to do this with you. There's a whiteboard. I'm not sure how to use the whiteboard with the Zoom. So what we could do here is maybe just have people think for a minute about, let's just do, I asked you in the homework to do this for both reversible and irreversible reactions, because one of the things that you have to remember when you're doing a reversible reaction is that the rate law for the backward reaction is not the same as the rate law for the forward reaction. In this case, I said to you to assume mass action kinetics. And so I'd like people to, maybe somebody could walk me through the two. We won't do all of it, but let's just walk through the forward reaction. A goes to B. And if somebody would like to unmute and tell us what their reasoning for, first what the rate law is, and then what the ODE for A would be from the reaction A to B, assuming mass action kinetics. Let's based on what we did again 2 weeks ago, and this was in both, as I say, both homework 2 and 3. And again, I think people are picking this up, but as you saw when I did it in class the other day, I made a mistake doing it. It's easy to make mistakes. And so practice is the best way to get it through. So would anybody like to just walk through the idea of how to do A to B? And if somebody wants annotation privileges to, if you have a drawing tablet, for example, or wants to type, I could give you annotation privileges, I think, on the screen so that you could actually show it. Otherwise, I have the answer on the next slide, but I want people to walk through it, thinking about it before we go ahead. Anybody want to take a stab at what the rate on the arrow A to B is?
Can you hear me?
Yeah.
So for A to B, I think the rate would be given by some rate constant K, let's call it Ka, I guess. Ka multiplied by the concentration of A squared.
Perfect. Okay. All right. And what about B to C? Somebody, Grant, you can do B to C, or does somebody else want to do it? Well, maybe let's stick with A. So what is dA by dt, given that?
Well, dA by dt, you also have to factor in the reaction of A to D.
Right, let's just consider the one that's going A to B for the moment.
Okay, then the ODE for the change in the concentration of A would be given by 2 Ka A squared.
Right, and it'd be a minus sign because you're
Yeah.
using up A. Right, good. And what about for B? What would dB by dt be?
It would just be negative Kb times concentration of B.
No, sorry, no, for the same reaction, for A going to B, not the reverse, not the reverse reaction.
Okay. For A going to B, the ODE for B would be given by just the opposite of A, so just positive 2 Ka A squared.
Okay, so that's the key thing to notice here. You're using up 2 molecules of A, but you're only producing 1 of B. So it dA by dt is minus 2 Ka A squared. But dB by dt is just Ka A squared. There's no 2. And that's exactly the thing that's easy to get confused about when you do this. You're using up 2 molecules of A to create 1 molecule of B. And so that's exactly the point that I want to make. And we all get caught with that. It's easy to look at it. You think, well, it's 2 on one side, it should be 2 on the other, but it's not. Okay. Does somebody want to do the B to C case? Somebody else want to do the B to C case? Thank you, Grant, for doing that.
Wouldn't it just be KB times the concentration of B, right? Because the stoichiometric coefficient is 1 or -1 for what we're losing. So you're just subtracting.
So dB by dt is what?
So we're just doing B to C.
B to C, yeah.
Then it would just be the KB times B.
Right, with a minus sign. You're
Right, minus, yeah.
And what
And then-
about for C? What about dC by dt?
It would be 3 times KB times B, yeah.
So again, 1 molecule of B is destroyed, you create 3 molecules of C. So the prefactors are different. The rates, the Ka or Kb times Ka times A squared, or the Kb times B is the same, but the prefactor depends on the stoichiometry. And so I think that's why it's a little bit, it's easy to get confused, because you expect if the rate law is the same, the prefactor should be the same, but the prefactor depends on which species you're putting it, which ODE species, which species is ODE you're putting it in. Okay, great. So that's what you get. And so I just want to emphasize that this is not rocket science. There's a rule, but it's easy to get confused by that rule. And if you get confused, you'll get the wrong answer. And the computer won't tell you that you got the wrong answer, because the computer will syntactically writing the other thing is correct. Now, if you write 2A goes to B as a rate law, as a reaction in antimony, it will handle those prefactors, the stoichiometry, automatically. So you don't have to worry about it. However, when you do that, that stoichiometry is handled reaction by reaction. And so something that I saw in a few homeworks was people who were used to writing ODEs were trying to aggregate multiple arrows in their reactions into one line of antimony. And it is possible to do that in some cases, but I strongly discourage doing that. It's extremely easy to make mistakes when you do that. And so for each arrow that you see in your diagram, I strongly encourage you to write a separate line of antimony declaring that reaction. Don't try to aggregate things into a single line of antimony. And some of the examples in the homework gave were situations where, in fact, if you do that aggregation, you get the wrong answer. So I think that that's something that I want to bring up here, because it's a general principle that when you're writing antimony, you don't do that aggregation. You keep each line separate. So let's do that now as an example. Here's one where, in fact, if you try to aggregate it into your rates into single lines of antimony, you'll get the wrong answer. So why don't we think about this? And there's another thing that we have to think about in this particular reaction, which is that there's a shorthand going on. And again, that shorthand is something that we have to be aware of and be prepared for. And so would somebody like to just start? Let's start on the left-hand side here with that supply arrow. And will somebody give me a guess, or not a guess, but tell me what the effect of that supply arrow on A is? So dA by dt equals something, not for the whole equation, but just for this arrow here, the K1 arrow.
Yeah, that's equal to K1, right? A is produced by the rate of K1.
Right. Now, it looks like it should be producing 3K1 because you've got that 3 there. And if I followed the rule that I had from the previous diagram, I would expect that dA by dt would be equal to 3K1. Because it looks like 1K is producing 3 A's, but it's not. And that's the reason that it's critical in this case that you have those lines be separate lines of antimony. Nothing goes to A at the rate K1. Nothing goes to 3A at the rate K1. Okay. The other thing that is important is don't combine in a single line of antimony the forward and the backward rates. Sometimes you can get away with that, but if the stoichiometry is inconsistent, it can be a mess to do that. And I noticed that some people were doing simulations where they got negative concentrations. And the moment you see a negative concentration in the simulation, you know you've made a mistake. And in every one of the cases that I saw in the two homeworks, in homeworks 2 and 3, people did that because they tried to combine forward and backward rates into one line of antimony. And that was not something that was consistent. So you should always be writing this as 4. In this case, you have 4 arrows, so you have 4 lines of antimony. Nothing goes to A, 3A goes to 2B, 2B goes to 3A, and B goes to nothing. 4 lines. So every arrow gets its own line of antimony. Okay. So let's walk through this now. Let's do, somebody give me the forward rate. What is dA by dt related to 3A goes to 2B? I can just.
So that one, you said for 3A goes to 2B?
Yeah.
So the ODE for that one would be -3 KF A cubed.
Right, perfect. Okay, let's just go down. Let's hear from people we haven't heard. Sean, what is the rate for B for that same reaction? 3A goes to 2B. dB by dt equals what?
I believe it's 2 KFA cubed.
Good. Okay, now why don't we go to the next? Why don't we go to the next one? Sean, let's stay with you for one more. Let's go down to the next one. What about 2B goes to nothing at a rate K2 times B? What's dB by dt?
Okay,
John,
so it's -2 K2 B.
right, so this is tricky. Even though it's written that way, that's a shorthand. And when you see supply or decay, you ignore the stoichiometry coefficients. So even though it looks like it should be 2 K2B, following our normal rules, when you have sources and sinks, you ignore the stoichiometry. So it would actually be dB by dt is equal to minus K2B. And again, I understand that this is confusing, but we have to, it's like spelling the English language. Sometimes we just have to learn things. And this is one of those cases. Great, thank you. So let's now go around, and who's next on our queue? Gabriel. What is the rate law now coming down for B? 2B goes to 3A. What does that do for dB by dt?
I'm sorry, what was it one more time?
So we are looking here at 2B goes to 3A, the backward reaction. And I want you to tell me what dB by dt is for that reaction, just that piece of it.
would it just be minus 2krb squared?
Perfect. And what about the dA by dt for that reaction?
That one I would be a little confused on.
Okay, so even though it's a 2 on the right, I'm creating 3. And so the result would be dA by dt equals plus 3 krb squared.
dA by dt equals
Plus
3
3.
plus 3.
The number just 3 times krb squared.
Oh, okay, got it. Thank
So
you.
I'm creating A, and I'm creating 3 molecules of A per unit of reaction. And so again, it doesn't balance. I destroy 2 B's and I create 3 A's. And so I appreciate people being willing to do this. I know it's a bit confusing. And so the best way to do it is to practice. The slides that I did 2 weeks ago have a lot of examples. I didn't go through all of them in class, but a lot of examples where just systematically you could work this through. Joel, go ahead.
Yeah, can I talk about the reasoning I used to not say that K1 goes to 3A or 2B leaves the simulation at a rate K2? Is that it doesn't make sense, right? It doesn't make sense that we adding 3A's because that just means that the rate is higher. It wouldn't make sense to say 3 things appear. It's the K1 is already saying 1 thing appear at this rate. If we need 3, we just multiply, we scale that by 3, right? That was the reasoning.
Yeah. Well,
I don't
that's
know if
right.
that helps people to understand that better.
I mean, another way to think about it is that the creation of A is happening independently. Now, if A were being supplied as a molecule, then maybe it would make some sense to think about supplying 2 units of them. But in that case, you wouldn't be supplying A, you'd be supplying some molecule which was 2 A's. And so I think you're right. Decay in particular happens at the level of individual molecules. And so unless you have a complex of B type BB, it wouldn't decay as a unit. But again, the notation is awkward. The other notation which we'll try to avoid, which you'll see quite often, is that here I've got the arrows labeled with mass action. I've got Kf times A cubed, Kr times B squared, K2 times B. But very often those arrows, if you're doing mass action, will only be labeled with the rate constant. And so you would see K1, Kf, K2, and Kr, and you wouldn't see the A cubed, B squared, or B. And you would be left to infer that if those are not written, you have to use mass action. Again, I will try always to write things out explicitly, but when you are reading the literature, and I know I was looking at some of the papers people were suggesting as sources for their possible projects, trying to look at them to see if there were potential issues that you might run into. And most of those papers actually do what I've just said. They would write this as K1 goes to 3A, 3A goes to 2B at a rate Kf, not writing the A cubed. 2B goes to nothing at a rate K2, not writing the B. And 2B goes back to 3A at a rate Kr, not writing the T squared. And so when you're inside of Herbert's textbook, it's a little bit protected because we worked hard to try to make sure that we don't have those traps. But when you look at these in the open literature, you'll find that people are pretty sloppy. Any other questions about that? I realize it seems in some sense extremely elementary, but as we see, it does take some practice to get used to. And if we put it all together, then our net rate for A is K1 plus 3KRB squared plus minus 3KFA cubed. dB by dt is 2KFA cubed minus 2KRB squared minus K2B. Notice that I have the prefactor 3 in front of both the B term and the A term. I have the prefactor 2 in front of both the A term and the B term. So the stoichiometric number in the front follows the species that I'm acting on. The exponent follows the source species. So the next thing I wanted to comment on about the homeworks is that I realize some of these homeworks can be long, and I'm often asking you to explain your results. And I realize that initially that seems like a bit of a trap, and especially if you spend a lot of time on coding, it may seem like extra effort for not much. But in fact, the questions that are asked, and it's not that you absolutely have to answer every possible question, but as the semester goes on, I will, if you want full marks on a homework problem, I will expect you to answer those questions. And the questions are usually asked in a way that is designed to try to help you understand not only the mathematics and the computing of a problem, but actually the meaning of it. And there's always a bit of a tension between asking those questions in a way that gives you the answer that I'm looking for, and asking it in a way that's so vague that maybe it's hard to follow. But I do really ask you to try to take those questions seriously. And I know that that means that it takes more time and effort. And as we go through the class, especially in examples in class, I hope we can talk these through and that you'll develop some intuition about what's a reasonable answer. I'd much rather have some answer that's your opinion, but don't ignore those questions. There was an open-ended question in homework 2, which was about finding online resources. I was hoping that people would find online resources that were not the ones that I listed, like KEGG. A few people picked KEGG examples and downloaded them. That was okay. But I did ask you to go a little bit further and say, what are the advantages and deficiencies of the source? Does the source include data on reaction rates or only on network architecture? Does it contain downloadable representation of the network? If so, does it use a particular format? And then I asked you to download a network and say what kind of network it is and what the network does and why you chose to include it. I should probably have also asked, as a general question, what kinds of networks are in that data source? Because some people went and found some networks, archives that I didn't know about. It sounded quite interesting, but didn't necessarily explain what kinds of networks were available in that source. And a lot of people went through this exercise and did exactly what was asked here, which was great. A few people found something, downloaded it, and that was it. Again, at the beginning of the class, I understand the time pressures and otherwise, but as the class goes on, I do expect people to try to make their best shot at answering that. In homework 3.3, there was a question like, describe the shape of the steady state curve as a function of I. And I specifically asked the question, is it linear, convex, or concave? And we'll come back to that later on. Pretty often I will ask questions like, what happens early on in the time series? Answers could be the rate of increases in time. The rate of increase is linear in time. The rate of increase is constant or decreasing in time. Or as I change this parameter, this increases. Or as I change this parameter, this increases faster than linearly. Those are the kinds of answers that I'm looking for to get a sense of the structure and meaning behind these numbers that were generated. As a request, and I realize that Canvas, just the way I can't get you good sources for the Canvas, uploading the problems to Canvas is a bit of a problem. I've been emailing everybody the homeworks. The homeworks are available on Google Drive. And I'm uploading the homeworks to the file section of Canvas where there's no problem with it. If you have any questions about what the homework is, please do ask. I've said repeatedly, and I will say it again, do not use the Canvas specification of the homework problem. Those are just there to upload the files. And in the future, that will be, now that I've said it again, if people do that in the future, I'll have to mark down for it. I also need you, in your responses to the homeworks, I need you to include screenshots of your simulations. Because if you just describe what you saw without showing it, it's very hard sometimes to understand what happened, especially if everything is right, that's great. But if things are not what you expect or right, then it's very hard to debug things. And I do ask you to upload your Jupyter notebooks as well, because it's very hard to give partial credit if there's a problem and I can't see what you did. And I realize that sometimes it's difficult to upload 2 files when you're doing your homework upload. If that happens and you have a problem with Canvas, email me and the TA with the files, and we'll get that taken care of. But we need to see your Jupyter Notebook solutions as part of your homework submission. I'd like to move on and walk people through, and I'm going to go around the room. There were a couple of questions about this rather open-ended problem that's due today, which was thinking about limits. And one of the key things that we need to do when we're doing mathematical biology, but engineering as a whole, frankly, or science as a whole, is to think about limiting cases. What happens when something is small? What happens when something is big? What makes sense? Sometimes that will depend on mathematics. Sometimes that will depend on our knowledge of physics, chemistry, or biology. Sometimes it will depend on our knowledge of the universe as it works as a whole. Sometimes it's anybody's guess. But very often, even if we don't know what happens sort of in the middle, we do know what happens when we have large or small numbers. And I wanted to walk us through these, and I'm just going to go around the room and let's discuss them. And I want people to think about answers for these. And again, the goal here is not to be right or wrong, but to begin to think about problems in a way that gives you a sanity check on your answers. Because when you write a computer program, if there's a syntax error, of course, the computer program will crash. But if you write a model that is syntactically correct but doesn't make any sense, the computer program will churn out numbers. And you have to have some intuition about whether those numbers are reasonable or not, a sanity check, in order to be able to understand whether there's a mistake or not, because it's not a syntax error, it's a conceptual issue. And so I will again go around the room and let's just walk through these, not taking an enormous amount of time. And again, if the answer is I have no clue, we'll move on to the next person. There's no shame in that. This list was actually trying to address some of the different kinds of questions one might want to model with the kinds of models we're doing, and also illustrate some of the different kinds of considerations that come in to give a sanity check, because it's not always the same kind of sanity check that we might want to do. Eden, do you want to maybe take a stab just at the beginning on population of humans on Earth as a function of time?
Sure. So I was thinking about this in relation to carrying capacity and birth rates and death rates kind of relative to that. So the parameter I was imagining varying very loosely was the size of the planet, where we can imagine if the planet goes to be infinitely size, we could imagine that the human population also infinitely grows. Whereas if the planet goes to having no size at all, we'd have no people. You can also imagine playing with the birth rate explicitly on a fixed planet, whereas if you have a really high value of birth rate, the planet gets filled up almost immediately. And if you have a really low value, it never changes. So two sides of the same kind of phenomenon.
Okay, so let's run with that and think about this a little bit more. We could go backwards in time and ask the question, what actually happened with the population of humans in the past? But let's go forward in time. And let's take the idea of carrying capacity seriously. And of course, this is a question that was asked a long time ago. I mean, Malthus was of course, the person who came up with this idea. Really, it's a question, which is, suppose that you have a fertility rate of 2.5. That is, for each generation of two people, the next generation typically has 2.5. Well, in that case, you expect to have an exponential growth in the population. So the first question is, what is going to happen if that happens? Is it possible for the human population on this Earth that we have here, if we can't expand the Earth the way you suggested? The Earth has some finite carrying capacity, as we point out. Technology might improve it a little bit, but what's going to happen in terms of, for example, resources per person if the population grows exponentially?
Yeah, usually I think this is modeled in forms of like density dependence, where you get this negative feedback between the existing population and the birth rate, which is, to your point about resources, there's only so much to go around, and eventually the resources per person are too low to sustain adding any more people.
Right. So what you're saying is that the population can't keep going up exponentially forever. So the population can't go up infinitely. So what could it do? There really are three options there, maybe four actually. What's one possibility? The population is going up exponentially, and now we start running into resource limitations. What's going to happen to our population?
One option is that it asymptotes at carrying capacity and stays there. One option is that it overshoots and then some people die and it undershoots, and then you could get an oscillation out of that. You can also imagine everybody dying, although I don't really have a good explanation for that one. And I'm not exactly sure what the fourth would be.
Well, you could in principle come to a stable or nearly stable state where you got a lower population. If the people somehow damage the system so that the carrying capacity goes down, then you could wind up having an overshoot, a collapse, and then some residual survival. All of those things have happened in history. If you look at, say, the Anasazi or the Maya, you had relatively high populations in. The Maya did it twice. The Anasazi did it once. That got into ecological trap. You had a population collapse, and then in the case of the Anasazi, you had a residue population of something like 1/20th of the original population that survived until European contact. In the case of the Maya, there was a period of a few hundred years where there was a slow residual population. The population boomed again and then crashed again. So that's more of your oscillation case. But the one thing you know is that the population can't go to infinity. It's got to reach a saturation. That saturation could be smooth and at carrying capacity. It could come down, could oscillate, or you could have extinction. So that's a great analysis, I think. Okay, let's go down. Lindsay, how about rate of chemical reaction A goes to B as a function of the concentration of A?
Well, if the concentration of A is 0, if there's no A, then the rate of the chemical reaction will obviously be 0. If it were like some infinitely concentrated species, the rate of the chemical reaction would be infinite. And in between, it would be some or proportional in some way to the concentration of A.
Right. In general, if all we know is that A goes to B, then each reaction is independent of every other reaction. And so the rate should be linear in the concentration of A. In reality, at some point, if we keep adding A to a solution, A will start interfering with itself. And so if the concentration of A gets to be enormous, the rate of reaction probably has to be less than we predict. But with that arrow by itself, we'd expect fundamentally a linear relation, as you outlined. Okay, Danusha, what about the rate of a chemical reaction A goes to B as a function of the temperature?
Hello.
Yeah, please go ahead.
So with the function of temperature, the rate of reaction would increase about like twice. But when you increase the temperature like drastically, it might stop the reaction. That's what I think.
Yeah. Well, so suppose we were at absolute zero. What would the rate of reaction be typically?
So if it's absolutely zero, then there won't be any change in rate of reaction.
Right, there shouldn't be any reaction.
Mm-hmm.
And as you point out, in general, chemical reactions depends a little bit on whether the reaction is endothermic or exothermic. We haven't said that. But as you say, in general, the rate of chemical reactions increases with temperature. On the other hand, if the temperature gets to be very high, the rate of back reaction may go up, it's possible, or A might fall apart and turn into something else, and you wouldn't have any A anymore. At some point, your molecular species will break down if the temperature gets too high. I suppose if you were in the inside a star, you would not only lose your molecules, you'd lose your atoms. And so, again, over a reasonable sort of room temperature range, we expect rates of reaction to go up as the temperature goes up. But there are limits to that. So that's great. Thank you very much. Okay, what about number 3 before? The rate of a chemical reaction 3A goes to B as a function of concentration of A. Who's next? Zachary.
I believe it would if A becomes really small, the rate would lower as a result, especially when the concentration is below 1. But if it's above that, then the rate would increase exponentially compared to the amount of concentration.
Okay, so what was our base assumption for reactions if we don't know anything else? Could increase exponentially, but we've been talking about mass action. So if this were a mass action reaction, what would the law be?
I'm not quite sure what you mean.
Well, for example, we just did this in the previous example. So if we have 3 molecules of A combining to make 1 molecule of B, we have a hypothesis about what the reaction rate form looks like, which is called mass action.
Okay. I mean, when we just multiply, wouldn't it just be K times A cubed, right?
Right.
So
exactly.
the concentration would be cubic compared to the concentration of A.
Right. Good. So that's our base assumption. Now that's what the math will tell us. And now we have to ask the question about chemistry. And it's fine, we can move on to somebody else if you'd rather. If the concentration of A is very large, do we expect the rate of reaction to be equal to mass action, faster than mass action, or slower than mass action? Somebody
Faster than mass action.
So somebody said you say faster. Does somebody else has done some chemistry have an idea about that?
I would expect it to be lower than mass action because mass action only works at small concentrations.
Right. And the reason for that is that the mass action is based on the idea of saying that there's a volume in space, and you need to know what the probability of having 3 molecules of A within that volume is. And as you increase the density of A, the fact that A occupies a finite amount of space means that you crowd each other. Your molecules crowd each other. And that means that the probability goes up at a lower rate than you would expect. And so what you expect is that at low concentrations, you'll see mass action. At high concentrations, you'll see the rate of reaction increase slower than Ka cubed. Now, there definitely are situations which are counter to that, but that's the classic expectation from chemistry. And again, what I'm trying to illustrate by these different questions is not that you have to know the answers to all of them, but that even something that looks relatively innocent, like number 2 and number 4 look very similar. But in one case, the reaction is independent of the molecule, the reaction of A to B is, the A's are independent of each other. And that is effectively independent of the concentration. And in the second one, the rate is dependent on the concentration, and therefore you expect to see a different result. And it's fine if you disagree with me. In other words, if you come up with an argument that for why the rate should go up faster than A cubed, I'm happy to have that. What I want to hear is your reason. Okay, let's take another one that's more biological. Let's see who's next on our window. Now the fact that I can't see the people is a problem. Who is not? Let's stay in the room. Okay. How about number 5? The rate of glucose absorption by E. coli as a function of external glucose concentration. And if you want to unmute so that people can hear you, I will mute my computer. Oh, you're not in the Zoom. Okay, so, okay, go ahead.
The lower bound for E. coli would either be the rate of absorption as the infection rate is when it's not being maintained as an active, or it's completely dead in the and the max rate of absorption would be always binds to the
So the answer that was given was that if the E. coli were dead, it wouldn't be absorbing at all. If the E. coli, if the concentration of glucose outside the E. coli is very high, there'll be a maximum rate. And so you'll see saturation. And so in that case, you'd expect that for low concentrations of glucose, the rate of absorption would be linear in the concentration. And then you would see a saturation of a maximum absorption amount at high concentrations. And that seems to me to be a good place to start. And I think that that's a reasonable hypothesis. And the idea of resting metabolism would perhaps give you a sense of where that saturation of absorption should be. There's a little bit of a sting in its tail that comes back to number 1. And if somebody else wants to answer that one, suppose that I put my E. coli in an environment with really a lot of glucose, what would happen? That's a biology question. Suppose I put my E. coli in honey, what would happen?
I don't know. I'm assuming something like death. Like if you put a human in too much oxygen, we're just going to die, right?
Yep, you got it. So then the uptake rate would be 0 through catastrophe, just the way if you had too many people on Earth, you could have an extinction event. And so in this case, there's the possibility that the glucose outside the cell breaks the cell. And then, of course, the rules have changed. And so you have an additional complication. And so typically what we're going to do when we do these kind of computations is we're going to assume what's called Fick's law, which is that the rate of transport across the membrane is proportional to the difference in concentration between the outside and the inside. And if we have diffusive transport, that's about right. We'll also probably assume that there is a saturation, so that there's some maximum rate of uptake. And that's also possible and probably true. But in reality, there could be these additional complications like too much glucose, the cell gets sick and uses less. Really too much glucose, the cell dies. So the rules can change on us in these limiting cases. Normally, we want the limiting cases to simplify our lives, but with living things, sometimes they make it more complicated. So thank you very much for being willing to do that. Okay, the next one basically follows up on the same argument that we just made, which is the rate of division of an E. coli cell is a function of temperature. Who's next on our list? Has anybody not answered one so far? I think we're back to Connor.
So once again, very simply, absolute zero. There should not be any division occurring. Probably low amounts of division as we get up to room temperature. Probably would expect a faster rate as we start getting up there, but then once we get to higher and higher temperatures, we should expect to see the cell breaking down, in which case it is not dividing.
Right. So again, absolute zero, the cell's frozen, may die, it may be able to come back, but it's certainly not going to divide. There's going to be some minimal temperature at which the cell is functional and is able to just persist, maybe not grow at all, but then as the temperature goes up, you would expect the growth rate to go up. What the functional form of that growth rate is, I really don't have any idea. Whether it's exponential, linear, or something else, I really don't know. Just the way that glucose absorption, we're typically going to assume that glucose absorption rate is linear in the concentration outside the cell or linear in the difference in concentration. But in the case of things like active transporters, it doesn't have to be for number 5. Here, and that's very hard to measure. You'd be surprised if you ask the question. If you ask the question, which is something you need, if you're going to do a cancer model, you're going to say, my cell has a certain level of glucose and oxygen outside of it. How fast does it grow? And the answer is, I have no clue. Typically, people will assume that that growth rate is proportional to the uptake. You'll assume that the uptake is proportional to the concentration. And then the growth rate is the concentration taken in minus the resting metabolism. But in reality, those uptake rates can vary by orders of magnitude, depending on what the state of the cell is. In the same way with cell division, we do know that E. coli divide faster at warmer temperatures over some range. And there's a simple kitchen argument for that, which is if it weren't true, refrigeration wouldn't work. And neither would freezing. If E. coli divided as fast in a refrigerator as they do on the counter, refrigerating your food wouldn't protect it from spoilage. If E. coli in the refrigerator divided as fast as they do in the freezer, then freezing your food wouldn't do any good. And Joel makes a comment, is it related to the volume of the cell? Is what related to the volume of the cell?
Well, you were mentioning about the cancer and saying I give X amount of glucose or X amount of nutrients. How, what is the growth fact? What is the growth rate? Can't we do a calculation by saying, let's look at the volume of the cell in different amounts of nutrients and see if anything changes by the amount of glucose exposed?
So the answer is that almost everything changes. And that's what's hard. It's not, or it's the growth rate of the cell. If I keep everything the same, the growth rate of the cell will increase as I increase the amount of glucose outside the cell, at least for small concentration. But almost certainly things about the cell will change in response to the glucose concentration. And therefore it won't be the same cell in terms of its state in the two cases. And so if I ask the general question, suppose that I'm making a cancer model and I have breast cancer cells and they're taking glucose up from the environment. I want to know what fraction of the available glucose do they take up per unit time? And typically you'll say, well, they take up 5% of the available glucose, something like this. And what you'll do is you'll tune it so that the growth rate that you observe in your simulation matches the growth rate that you see in the experiment in terms of the rate at which the cells put on mass, because that's something that can be measured. But the actual uptake rate of glucose is actually pretty hard to measure. You can measure it effectively by using radioactive tracers. That's basically the only way to do it.
So it would be better described if it was a partial differential equation instead of an ordinary differential equation, right? Because we assume that the function will change in function of the what is presented, right? Of the initial states.
Right, but you still have to have some functional form that tells you, given the concentration of glucose inside the cell and the concentration of glucose outside the cell, what is the transport rate of glucose from outside to inside? And the answer is there is no simple mathematical form that tells us that. It's going to depend on details that we don't have in our model. And typically we're going to assume a linear transport rate, a Fickian transport rate. And that's true typically for diffusive systems. It's not going to be true when there's active transport, which it's true for which exists for a lot of molecules. Certain things have to be true. If there's no glucose outside the cell, the rate of absorption has to be zero. So at the concentration of zero, the rate of glucose absorption has to be zero. So for very low glucose concentrations, we expect a linear response. But above that, we don't really know what's going to happen.
Professor, to add to that topic, I would say, like, in case when there is an excess of glucose, the cancer cell goes to oxidative stress and they store the glucose so that it can be consumed later on when there is a deficiency of glucose in the healthy cell or in their environment. So
absolutely.
Yeah.
Go ahead. Sorry, go ahead. That's a good comment.
Yeah, so as of now, we don't have a legit paper on any literature that is saying what is the exact activity of cancer cell in presence of high glucose. Because in some circumstances, those glucose is converted or been mixed up with iron or anything else that makes this cancer cell to survive for a longer period of time and convert the healthy cells into cancer cells. And at times they just resist the apoptosis and they do not die at all. So yeah, it's still in study. And I want to just comment on that.
Right. Thank you. That's a great point. So when you have glucose outside the cell can essentially do a couple of things. It could leave the glucose outside the cell and not take it up at all, although some glucose will cross the membrane by diffusion. It could actively import glucose, and the rate of import is something that the cell can regulate. Once the glucose is inside the cell can do multiple things with it. The cell could use the glucose and convert it into ATP, basically into energy. The cell could use the glucose and build components of the cell, basically doing synthesis, either for maintenance or for growth. Or, as you point out, the cell could turn the glucose into something like glycogen, store the glucose, and then have a reserve for the future. How the cell allocates the glucose coming into energy production, synthesis, and storage is something that's highly regulated. And how that regulation works is going to vary from cell to cell. So in our typical models, we're going to handle this in a very simple way. We're going to make simple assumptions about it. But in fact, in reality, that's a very complex set of questions that, as you point out, are not well understood. You mentioned metabolism and the cell going from aerobic respiration to glycolysis. That changes the rate of use of glucose. It changes how the glucose is used. And those are decisions that may depend on the cell state, on the oxygen level and on other things. And so I just want to point out that this apparently simple answer, which a physicist would say, well, the rate of glucose absorption is proportional to the difference in concentration between glucose inside the cell and outside the cell. That's a reasonable place to start, just the way mass action is a reasonable place to start. But in fact, things get more complicated pretty fast. And so I appreciate that your comment is a very helpful one.
Thank you.
Again, I don't expect, when people answer this question, I don't expect people to write a dissertation on it, but different people have different backgrounds and experience. And so it's worth thinking about these questions. There were 3 other little examples here. And let's just do number 1 and 2, because those are going to be things that we're going to come back to pretty soon. And in this case, we have some concept of, in this case, it's written as a signaling reaction, although it could be also thought of as a gene regulatory reaction. We have our 2 kinds of arrows here. We have our transformational arrow, S1 becomes S2. And we have a regulatory arrow, A regulates the production of S2 from S1. And in our world, we're going to use the notation that a lollipop arrow is called an activator, and a T-headed arrow, a blunt-headed arrow, is called an inhibitor. And so, where were we in our cycle of answers?
Can I ask a question about this? Yeah, about this A here. Is it regulating? Because the sense of regulation has a different connotation in my head than for example, if it's a symbol of like a transistor, right, where we have emitter, base, and that's the gate, and energy just flows from S to S2 if A is activated, right? How we interpret this again?
That's exactly the question I want you to answer. And I think you were the next on the list, so you get to try to answer it and see whether if you have trouble with it, your classmates can help.
Right. If I consider it as a gate activator, the concentration of A is definitely the limiting factor here, right? Because the more A you have, more reaction, and S and S1 too, right? The more S1 and A you have, the more S2 you produce. Now, if it's just a catalyst or accelerator, then S1 goes to S2 independently, and A is just making it go faster. So the concentration of A has less importance in this reaction than if you use just as a gate.
Well, so it may not, even transistors leak, right? Even if I don't apply any voltage to my gate, there is some current across my transistor. It's called the leakage current.
True.
And so you're asking exactly the right questions here, which is, suppose I had no A at all. What would I expect the rate of S1 going to S2 to be?
Very small or 0. One of the two.
But not necessarily 0. It could be small. And whether that small number is significant or not is going to depend on the context in which S1 and S2 find themselves. In reality, there's probably some rate, even if it's a small one. And if we do analysis a little bit later on of latching behavior, we'll discover that basal rate, just the way basal metabolism for the cell is important, that basal rate of S1 going to S2, even when A is 0, we'll typically assume that rate is 0, but if it's not, it can have a big effect on the result. Okay. Now suppose that now you've said it's an activator, so by definition, if it's an activator, the rate at which S1 goes to S2 should increase as the amount of A increases. Okay. Now suppose that I have really a lot of A. What happens to the rate between S1 and S2?
It would increase, but now it's dependent on S1, right? Yeah, the number of S2 produced will depend on the number of S1. even if you have a lot of A's.
Right. So if A is very big, does the rate depend on A anymore?
No.
There's a maximum rate of production of S2 from S1 for large A.
Mm-hmm.
And so what I expect is what's called a sigmoid. For small values of A, I have some basal rate of production. There's some region in which the rate of production of S2 goes up as A goes up. And then if A is big, the rate becomes independent of A. There's some maximal rate of production. You could imagine a little bit like our glucose example, that if you really had too much A, it would mess up the whole system and break it, and then you wouldn't have any S2 produced anymore because A would swamp the whole system. But we don't usually consider that limit. Let's come back to the last one, which I'm going to skip that very last one because we're going to do that as an exercise a little bit later. But let's do the inhibitor case. Does somebody, who's next on our list? Does somebody want to walk us through the inhibitor case? Let's see who came after. Hey, Joel, Sean. If we have an inhibitor, our S1 goes to S2, it's inhibited by R. Suppose we have no R. What do we expect our rate of S1 to S2 to be?
So if there's no inhibitor, then S2 would just increase as a function of S1.
Okay. And so if I increase the rate of amount of R, what happens to the rate of production of S2?
I'm assuming it'll go down to 0, but this basal case that you talked about previously, I guess somehow that still plays a role, and maybe there's some S2 that still gets generated, but probably very small.
Yeah, that's reasonable. But there has to be some level of R beyond which R doesn't have any more effect. I mean, if it's going down and it can't go negative, it has to saturate somewhere. In the case of the first one, at least conceptually, it could go to infinity, although it's not going to. In the case of an inhibitor, at some point, you can't reduce the rate to less than 0, and therefore there has to be some amount of R beyond which R has no effect. So again, these basic relationships, and we'll come back to that in a class or two, knowing that the rate is 0 at 0 and finite at infinity and increasing, means that there aren't that many functional forms we can use to describe it. And so actually just knowing these limits actually allows us to do a lot of detailed mathematical biology without any measure. And if that weren't the case, most of the things that we do wouldn't work. There are going to be some exceptions, like with gene regulatory networks. The way we think about these things is a little bit strange. But we spent quite a bit of time on this, but I hope it was useful for you to walk through these together, because they're not trivial questions. They're questions that require a little bit of thought. Probably everyone in the room has thought about some of them, but somebody could raise his hand and say, or her hand and say, I've thought about all those questions already and knew all the answers beforehand, which is fine. But I hope that at least some of them were thought-provoking a little bit and help people think about how to think about modeling a little bit. Okay. Another comment on the homework, which is, and I probably should have put a little line here reminding you, m.simulate minimum time, maximum time, comma number of steps. And so we've been doing simulations a lot where I've asked you to change a parameter, change the rate constant, change a value, and I'll say run it and see what happens. And people do that, and that's fine. But you come into immediately into a problem. If you want to know what the steady state is, the time your system takes to get to a steady state will very often depend on those parameters. If I have a rate constant and I reduce one rate constant, A goes to B and the rate K times A, and I change the rate K to be a 10th of what it was before, the system will take 10 times longer for the initial value of A to get to the same final value of A. And so that means that when I change my parameter values, something that happened, I may have picked my parameter values initially so that I see my curve come up and saturate in the middle of my time. I now reduce my rate constant by 10, and I'm still just seeing things come up at the very beginning. Well, if I want to know what the saturation value is, I have to change the time scale. I have to run the simulation for 10 times more time steps. Similarly, if I made my rate 10 times faster, everything might be over in the first 1/100th of my time interval. And if I want to understand what's happening, I would have to stretch my time axis in the x direction. And so when you're doing simulations and you're exploring the time behavior of your system, you may have to change the time over which you're simulating to be appropriate for the parameter values you've chosen. Sometimes, once you know how the system behaves, you could do that automatically. You could adjust the maximum time of the simulation in response to the parameter. But in general, you're going to have to do some exploration. You'll have to run it and say, gee, everything was over before I could see it. I'm going to reduce the maximum time in my simulation by a factor of 10. Or gee, my simulation was just getting started when I was done. I'll have to increase the time by a factor of 10. And so it's quite important that you actually look at your results and adjust your simulation time interval to be appropriate for those results. And how do you know in advance? The answer is you don't know in advance. Sometimes you can actually calculate it, but in general, we're going to assume we're not doing analytic calculations. You have to look. And if the question is, what's the long-term behavior? You're going to have to adjust the duration of the simulation so that you see the long-term behavior. And I know that that's something that you have to learn how to do, and it's one of the things that we have to learn together as part of the class. I strongly recommend running a few quick simulations, quick and dirty simulations, to get a sense of how the system behaves, and then adjusting your timescales to be appropriate after you've gotten a sense of the initial mapping. Sometimes you'll know, gee, as I change K, the simulation time scales with K, and then I can actually put into my loop, when I'm looping over values of K, I can change the maximum simulation time. Another thing that happened in a fair number of simulations, especially when you tend to make rate constants large, is that you'll see jagged or discontinuous behavior in your variables. And chemical concentrations never change discontinuously. And so if you see things that look like steps or jumps in the concentration for ODEs, one of two things is happening. Either you've made a mistake in your rate constants, and so one of those rate constants is diverging, has a 0 in the denominator. And none of the things we've done so far should have that. Or the step size we're using is too large, because the step size is maximum time minus minimum time divided by the number of steps. That's how we specify the simulate function. And if we make this number of steps too large, then the numerical integrators we're using are going to give us wrong answers. And so if you see jagged or step-like behavior or jumps in your simulation, that's almost certainly because you're not using enough integration points between your steps. And so if you said, I'm going to simulate between 0 and 100 with 1,000 points, you might try simulating between 0 and 100 with 10,000 points. And if that still doesn't work, simulate between 0 and 10 with 1,000 points. If that doesn't work, try to simulate between 0 and 1 with 1,000 points. And if that doesn't work, you pretty well know that there's a mistake in your specification of the simulation and the model structure. And so that's a basic workflow for debugging these things. And so whenever you see jumps in your simulation, especially at the beginning of a simulation, you have to first ask the question, is the time step appropriate? That is the number of points I'm using enough to smooth things out? And if that doesn't fix the problem, it means that there's something in the way you've defined the problem that isn't what you expect. It means the model has an error. And I know a couple of people saw that kind of behavior, commented on it. And I think that that was great that people noticed it. And I'm talking about it now so that the next time you see it, you can begin to think about what it means. Occasionally, very occasionally, those things are real. An example where that kind of thing can be real is in an action potential, where the opening of the ion channels is very, very fast compared to the later stages of the ion channel behavior. And so when you fire an action potential, the potential drops really, really fast. And that's a pain to do in this computer simulation, because if you make your delta t small enough that you catch that early phase of the action potential, your simulations get really, really slow. In some cases, people will use adaptive time stepping methods to get around that. Sometimes people will tolerate the slowness. Sometimes people will smooth out and fuzz out the opening of that action potential to fix things. And so it's not that you never get this kind of thing happening in biology. It does happen. But in the simple examples that we've been working with so far, it doesn't happen. Mass action doesn't give that to you. And so when you do see it, you should be suspicious. Not that you've made, not just definitely that you've made a mistake, but when you see behavior like that, you should first ask the question, is there a problem with the numerics in time stepping? Secondly, is there a problem with the way I defined the problem? And then if the answer for those is no, then you have to ask the question, is there something fundamentally about the structure of this biological problem that makes it hard to solve? What are called stiff equations. And we definitely will run into those. And the neuroscientists will run into them more than people doing gene regulatory and signaling numbers. But those things are going to come back, and I'll come back to that a little later in the class. Any comments or questions about that? Again, if I presented this material before you did the simulations, I don't think it would make any sense to people. You have to have done them to some extent before this kind of question, before these kinds of arguments, I think makes sense. So I'd like to actually follow on with that with a simple example that will illustrate some of these points. It illustrates a couple of things. We did a part of this in the homework, I actually, when I was teaching this material in some workshops, I did this example because I think it's actually a nice one. And I'd like people to fire up Tellurium. I've talked for an hour and a half. Usually my rule is I don't try to talk that long. But of course I haven't been talking, just talking, we've been discussing. I'd like to do a little exercise, which is a cascade reaction, a very simple cascade reaction. And I'd like to do an exercise where we explore, and I'm having this terrible feeling of deja vu. Have we done this exercise in class?
I don't,
No.
yeah, I
Good.
don't, I think we
Okay.
did something similar to it in the CompuCell class, which might be what you're
Okay,
thinking
that's
of.
good. Okay, thank you. I've been teaching this material so many times, I'm not mapping which, I repeat myself a lot these days as I'm getting older. And so if you find me repeating exactly the same story, I will not be offended if you say that's a great story, you've already told it to us. Okay? So please don't be shy if I'm repeating something that I said last week. If I say I know I'm repeating it last week, then I'm saying it a second time because I want to. But if you could ask me politely, are you sure you want to be telling us exactly the same thing again? So don't be shy about telling me if I'm repeating myself, okay? So let's fire up tellurium. And I want you to write a chemical reaction cascade. A goes to B, goes to C, goes to D, goes to E, goes to F with mass action law. And the one thing that I want to be a little bit different is that we could call the reaction rates, let's use numbers here. And I don't know why I use K2 for J1 and K3 for J2 and so on. You could number them 1, 2, 3, 4, 5. Actually, I do know why, because I want to then have a source of A, which would be K1. That's why they're numbered in front of it. Could have called it K0. But I want you to write a series of reactions. A goes to B at a rate K2 times A, B goes to C at a rate K3 times B, and so on. We'll start with only A. But the trick here is that I want my parameters to have a geometric ratio. So we'll say K1 is 1. K2 is K1 times our ratio. K3 is K2 times our ratio. K4 is K3 times our ratio, and so on. And I'm not actually sure that there are any biological systems that have this precise numerical structure to them, but it does have some rather nice properties to it. And so I would like people to do this. So I'm going to give this as a little home assignment now. Can people please fire this up and try it out? If typing it is too much, I put into the Google Drive, it's called homework 4 cascade equal K demo with max v2.py. But if somebody is an expert on Google Drive, I probably need some help, because I managed to, there was a Google Drive update the other day that clobbered my settings. I accidentally reset Google Drive so it did mirroring of everything. And Google Drive then happily loaded 2 terabytes of junk onto my laptop, which is now out of memory. And I don't know how to get rid of that junk without deleting the files in the cloud. So I'm sitting here with no disk space on this computer, and Google syncing has been turned off temporarily. And I tried to manually force a sync of that file, but it may not have synced. On the other hand, typing it by hand isn't too bad. So why don't people take a few minutes to type this or trying to upload it? Either way, somebody can check the Google Drive and see if it's there. And if it's not, then we'll all have to type it. It doesn't take more than 3 minutes or 4 minutes to type. You can either type what you see on the right, or you can do it from scratch, which may be fast. So I'll give people a couple of minutes to do that. I haven't been using the polling very often, but I don't have. All right, I can't use polling. It looks like the way Zoom is configured, it won't let me do it. So maybe when you're done, raise your hand so I can get a sense of how much time. And if there are any questions about the task, that's fine. Wow, that was quick. Were you able to upload it? Did the upload work or did you type it that fast?
Typed it.
Typed it.
Okay, well, let's give people a few minutes. You're fast typist. Let's give people a few minutes to make sure everybody's caught up. You able to get that to work?
I had a GitHub Copilot, so it just kind of figured out the pattern and just auto completed like half of it.
Yeah, well, that's right. I mean, even if you just type one and then cut and paste and just change 1 or 2 characters per line, that also works pretty well. If your AI will actually do the updating for you, that's even better. I like that.
Professor, I have one question.
Yeah, please.
Yeah, so while modeling, like how do we define the rate values? When we supposedly we are like going from A to B and the value for K to A, like how do we define the value for K2? So like it should be like randomly 1 or like how do we define it? It should be proportionate to the other rate constants or like how?
Well, so the operative word there was randomly. Things should never be randomly something unless you're doing stochastic simulations.
Mhm.
A rate only matters in respect to what your time units are. And since in this simulation, I haven't said whether our time units are seconds, minutes, or years, I don't know what K1 equals to 1 means. What I do know is that a rate has units of per time. And so a rate has conceptually is 1 over time. And so if my time units in this simulation were minutes, a rate constant K1 equal 1 means that whatever the reaction is that I'm modeling, and this is only, by the way, for the case of first order reaction. This is one of the problems with rate constants. They have units that differ depending on what the stoichiometry of the problem is. But in this case, when I only have A as my argument, K1 times A, the units of K are concentration per time. And so the actual value of A, K, has 2 components, the units of concentration that I'm using and the units of time that I'm using. In this case, if K1 if I'm measuring time in minutes, K1 has the property that it means that things happen over a period of about a minute. If I used a time unit of hours, it would be things take about an hour to happen. If I had K1 equal to 10, it would mean that it takes about 6, and I'm using the time units of minutes, it means that the reaction takes about 6 seconds to happen.
Okay.
So to ask the question, what is a reasonable value of K1? The first thing I have to do is what is my time unit in my simulation? And then I have to ask the question, how long does the thing that I'm modeling take? And the value of that rate should be 1 over that time. Maybe twice that or half that, but on the order of that. If K1 is multiplied not by A, but by A squared, then things are more complicated. But it is linear rates, that's how you could understand. So if you know that if your rate is the rate at which your cell grows, and you know that the cells double every 24 hours, and your time unit is in your simulation is a day, then the growth rate of the cells will be about what? If your time unit was an hour, your rate would be 1 over 24. If your time unit was a minute, then your rate would be 1 over 24 times 60.
Okay.
So that's
So
an
for
excellent
instance,
question.
The equation, sorry, the reaction which you have shown in the PPT, like how do we define for this kind of equation? If it's given like we don't have a legit value for A B conversion, like A to B conversion or B to C conversion, like how do we define the rate ratio? Like, do we take it over hours, like using hours or minutes, or like how?
Well, so if we're mathematical biologists, we make everything to be unitless.
Okay.
We would divide our time by a reference time. We would divide our concentration by a reference concentration, and typically try to make all of our time scales and length scales to be as close to 1 as possible.
Mhm.
But in an abstract model of this kind, you're right, there is nothing that guides us to say, does this reaction from A to B take a day, a year, a minute?
Yeah.
It's purely a mathematical form. And so in that sense, we have no way of knowing what this means, mapping it to the real world, because until we apply real units to it, we cannot answer that question. That's a very good observation.
Mhm. Thank you so much.
Okay. There's still a couple of people working on it. Is there anything? I mean, I hope the conversation isn't distracting you too much from getting the model working. Is anybody having any trouble getting it working? Joel, how's it going?
Oh, I'm done with it. Yeah. I just lower my hand because you asked the question. I thought better lower my hand so people can.
Okay, so let me then maybe put it a different way. Is there anybody who is not done? Okay, everybody's done. Here I have been sitting waiting for everybody to raise their hand, and people had already been done. Okay, good. So what did you find? What did it look like? Somebody tell me what it looked like.
It looks like a bunch of, I guess like humps, or I don't know, like it looks like Gaussian distributions. But except for A seems to come down like an exponential or logarithmic curve, but all the other ones seem to kind of have humps where B has the peaks the soonest and then F peaks the latest.
Great. Perfect. That's good. So this is practice in this question of describing what you see. And so you brought up a big point. What is it we can say about these curves? Did everybody get a curve that looks like this, more or less? Did anybody get something different? Okay, you got this. So you made two very good observations. We see a bunch of humps. When we see a hump, there are about 3 things that we can identify about a hump. There really are only 3 things. There are potentially a few more, but fundamentally there are 3 things about a hump. And you've mentioned 2 out of 3 of them, and you've mentioned the 2 most important ones. If we have a hump, we can ask, what's the maximum value of the hump? And the second thing we can ask about it is, when does the maximum occur? And the third thing we might ask is, how symmetrical is the hump with respect to time before and time after the maximum? Is it symmetrical between early times and late times, or is it skewed in one direction or another? And you also pointed out something that's very fundamental, which is that the time course for A looks fundamentally different from the time courses for B, C, D, E, and F. And as you pointed out, we see a series of humps. The peak times for the hump 1 is before the second one. The peak time for hump B is before C, is before D, is before E, is before F. And the maximum amplitude of B is bigger than that for C, is bigger than for D, is bigger than E, and is bigger than F. And so you've already identified two critical things. We might also see that F is almost symmetrical forward and backward time, and B is sharply peaked towards the early time. So those are some of the things that we might observe. And then we could ask the question, how do we quantify this? And I think in the code that I uploaded, if I remember right, I actually wrote some code that finds the time of the maximum and the amplitude of the maximum. And that's a nice exercise for yourself. I didn't assign it yet because it requires a little bit more Python. Although if I look at people's homeworks, people are pretty sophisticated in using Python to manipulate arrays and NumPy. NumPy has a function you can use that will find the time of the maximum in the time series and the value. So you can pull out a column of your output of your simulation and ask NumPy to give you the time and the value of the maximum. Or you could iterate through it by hand and find it by hand. What's interesting to me here is that if I actually find the times of the maxima and the values, the times have a nice behavior. The time of the maximum of the A peak is 0, it's always going down. B peaks at a time of 1, C peaks at a time of 2, D peaks at a time of 3, E peaks at a time of 4, and F peaks at a time of 5. Remember that our rate constants are 1, 1, 1, 1, and 1. And what I said about rates is that those rates are 1 over the time. So the first thing takes a time unit of 1. The second reaction takes a time unit of 1. The third reaction takes a time unit of 1. I'm seeing exactly that when I look at my times at my maxima. It takes 1 time unit for B. For B to go to C, it takes 1 more time unit. For C goes to D, it takes 1 more time unit. For D goes to E, it takes 1 more time unit. For E goes to F, it takes 1 more time unit. And so if I were going to ask you to describe what you see, these are all things that you could describe looking at this picture. It looks fairly simple, but there's a lot going on. And there is a systematic way to think about these things. Where are the maxima? When do they occur? What are their relationships? Or if there were a dip, you could say, where are the minima? Or what are the minimum and maximum values? In this case, the minimum value for B, C, D, E, and F is all 0. So that doesn't tell you much. So that's not an interesting question. For A, the initial value is its maximum, and its final value is 0. So the minimum value is 0 for everybody. So that doesn't tell us much. But the max value and the time of the maximum is significant. If I look at the values of the maxima, it's not quite so obvious what's going on. But if I and there I don't have an immediate answer. You could try to fit the maximum value versus the generation number. You might guess, well, maybe the maximum value is 1 over the generation number. Well, in that case, you would expect the maximum value times the time of the generation number to be about constant. 10 times 1, 3.7 times 2 is 7.4. 2.7 times 3, 6 plus 7.6, it would be 8.1. It's not quite right. It's not quite 1 over the value. But you could ask the question, can I come up with a functional form that gives me the values of the maximum? Okay. So now that we've done this, I want some people to change the value of R, that ratio. And let me remember, unfortunately, the way I've got this set up, I can't see it. I can't remember whether I do bigger than 1 next or smaller than 1 next. I think the next, why don't people try making the ratio 2. Make that ratio between the successive ones, not 1, but 2. So the rates go up as we go down our chain. I think I'm going to be backwards. I think I did it the other way. But I don't want to show you the answer. And I think if I go to the next slide, I've got the answer beforehand. So it takes the fun out of it. So try it both ways. Try r equals 2 and see what happens, and try r equals 1/2 and see what happens, and be prepared to tell me about that. I mean, doing the changing the value takes you 1 second. Looking at it and thinking about it takes a bit. So somebody let me know when you're ready to go on. Which one I did? Okay, the first one I did was r equals 2. What happens when you set r equals 2? Anybody? How is it different? Zach, I think you raised your hand. You get to tell me what happens when r equals 2. How is it different from r equals 1?
Well, for one thing, it happens much faster before everything steadies out. Also, it seems like the humps overlap each other more in time, and the decay between B to C to D to E to F is more significant. So the hump, and also the humps are smaller too. So even B is about half the size of what it was at 1, and all the other ones get progressively smaller, and they're all skewed to the left.
Perfect. So you've just done an incredible job of explaining what you saw. In the homework problems, when I say, what did you see? Those are the kinds of answers that we're looking for. That was great. Thank you. And I like this problem a lot because it gives you a good opportunity to practice those things in a controlled environment. So here was r equals 2. And as you say, the first thing you notice is that the peaks get smaller much faster as I go down my generation. The second thing is if I go from r equals 2 to say r equals 5, what I notice is that the time of my maximum for r equals 2, my maximum time is 0.35, 0.5, 0.57, 0.61, 0.62. So the B peak is a little bit earlier than the others. But if I go to a value of 5, for example, the peaks happen almost all at the same time. And as you point out, the amplitudes go down almost exponentially now in the peak order. The amplitude goes to about like the r to the minus I, where I is the peak order. So that's great. Thank you. Okay, let's go the other direction. Let's make r 0.5. And you could try 0.1 too, if you want. What happened? Give it a shot, and then somebody else see whether you can describe what you saw.
So inverse to what Zach was just saying, it seems that the peaks are much closer together in terms of scale. So when I set r to 0.5, it looks like, you know, the B peak is at around 5, and the following peaks are still going down, but are pretty close. And the reaction takes significantly longer. So I had to run my simulation from 0 to 500 instead of 0 to 10.
Okay, what about the time intervals between the peaks? Are they uniformly spaced in time now or not?
They are not. They're each peak it takes longer for the next one to occur.
Yep. So here I did 0.5, and this was my result. As you see, in this case, as you say, the value of the maximum goes down a little bit, but not by very much. B is 5.46, 5.4757. If I go to 0.2, for example, the amplitude of the peaks is almost identical. But the time intervals now are going up exponentially. Not perfectly, but almost. 3, 8, 18, 38, 80. It's almost a factor of 2. 4, 8, 16, 32, 64. And so this is very interesting. With the same structure of reaction, by changing that one number, the ratio, I can have peaks that decrease in amplitude like 1 over the peak order, which are equally spaced in time. Time 1, time 2, times 3, times 4. So I could generate pulses uniformly spaced in time, but with slowly decreasing amplitude. By making that ratio 2 or 4, I can have all my pulses happen essentially at the same time, but with exponentially decreasing amplitude. By making that ratio 0.5 or 0.2, I can make my peaks all have the same amplitude, but the time of my peaks stretch out exponentially. So that's a pretty impressive range of behaviors. Uniform time spacing, all at the same time, or exponentially slowing down in time. Uniform amplitude, harmonically decreasing amplitude, and exponentially decreasing amplitude. I can get all of those different behaviors from this super simple cascade reaction. And in biology, you'll often see this kind of cascade. A goes to B, goes to C, goes to D, goes to E, goes to F, goes to G. And you'll say, why not just go from A to G in one step? Well, sometimes it's because you have to have a lot of intermediate chemicals. Sometimes it's because doing these steps allows you to have very careful control over the amplitude and timing at which things happen. And in the homework problem, the one I did from Herbert's textbook, he asked you to do a simple version of this and then change just one of the values, not change all of them together, but just change one of those rates. And what you saw was that the equilibrium amplitude of the two concentrations flipped when you did that. And there's a concept in biology called a rate limiting step, where if you have a bunch of cascade reactions like this, where suppose the rates were all 1, K1, Q equals 1, K3 equals 1, K4 equals 1, K5 equals 1, K6 equals 1, K7 equals 1. And now I make K5 small. I make K5 0.1. What I'll find is A, B, C don't matter. But when I go, and there's a typo I see here, I've got C goes to C. It's a mistake. If I make K5 small, what I'll find is A goes to B goes to C, of course, doesn't change. Upstream doesn't change. But then things get slowed down when I go from C to D because K5 now takes 10 time units. And so the rate of the whole cascade is controlled by the slowest link. And this comes back to the question that was asked earlier about how do you know what the right rates are? Very often, actually, in these kinds of reactions, there are only 1 or 2 constants that actually control the rate of the whole thing. You have a long cascade, the slowest rate is the one that controls the time the whole thing takes. The other ones have some effect, but not a lot. The other thing you'll notice about this one that we're doing here, where the exponentially distributed times, is that there isn't a single time scale I can use to observe all of these things at once. If I use a time scale, as you pointed out, of 1,000, then I can see how my F curve behaves very well. But if I look A, B, and C, they're all scrunched together in the beginning. If I stretch things out to look at time, say, between 0 and 50 or 0 and 100, I can see A, B, and C, but my F curve hasn't even really gotten started yet. And so in this situation, I may have to do multiple simulations with multiple time windows to be able to understand what's going on. So I think this exercise, I hope, gives you some practice in adjusting your timescales on your x-axis, describing what you see in terms of the main features that you can identify. And so here's sort of a basic rule for what to do. If you see a time series, ask the question, what are the features that I could pick? What are the features I could pick? What's its value at time 0? What's its maximum value? What's its minimum value? What's its value at time equals infinity? If it's got a maximum, when does the maximum happen? If it increases and then saturates, what time is the maximum rate of increase? Is it symmetrical or not? These are the kinds of questions you can ask. And then if you've asked that about one time series, you can ask that about the relationship between them. How do the peaks change in amplitude? How do the times of the peaks change? And so those are the kinds of questions that I'm looking for you to ask for yourself and to learn to ask for yourself as you go forward when I ask these open-ended questions about what do you see? And so I hope that that's a helpful set of things to do. Again, until we start seeing some simulations, I think it's difficult to talk in the abstract about what it is you're looking for. But when you see it in front of you, I hope that maybe those kinds of questions are more meaningful. So we've overrun our break time a little bit. Why don't we take a 5-minute break, and we'll start back here at 6:12 by my clock, and we'll continue from here. And I'm not going anywhere, so if people have any questions that they want to address during the break, that's fine, but we'll be officially off the clock now for 5 minutes.
Hi, James. I have a question.
Sure.
In part 3 of the homework on questions 2 through 4 that we reviewed, I was still a little confused. In particular, especially part 4, I was confused as to what you were saying was wrong with my answer.
Well, probably we shouldn't talk about your specific, what I said was right or wrong on a live broadcast.
Okay.
But if you have a question about the problem and its solution, I'm happy to talk about that. So what was the question, and what was the issue that you wanted to address?
So I guess for question 4, I'll just go with question 4. So the rate, so it's the rate of the chemical reaction 3A to B as a function of the concentration of A. So if A were high, then the rate would increase, and if A were low, the rate would be lower. And my understanding was that it's dependent on A cubed.
Right.
Right.
So I think, and so your concern was that I said that what you said. Oh, so this was just at the beginning of class when you said when I asked you what it was, and I said that wasn't quite right. Is that what you mean?
Yeah, I didn't understand what was wrong.
Okay. Because you said that the rate goes up exponentially with the concentration, and the rate goes up as the cube of the concentration, which is a power, not an exponential. The rate goes like A cubed, not 3 to the A.
Oh, okay. I see. I guess I misused the term exponentially then.
So sometimes we use the term exponentially to mean just fast. But in the mathematical biology class, when we use the term exponential, we really mean exponential. And so in this case, you were absolutely right that the rate of reaction goes up as A goes up. But the rate at which it goes up is A as the cube of A, not not e to the a.
Okay,
An
I see.
exponential increases faster than any power law. And there are reactions. If we ask the question, how fast does a reaction change as a function of temperature? In certain regimes, the rate of reaction will in fact increase exponentially with increasing temperature. So there are situations in which reaction rates increase exponentially with a parameter. And so I was just trying to be careful about the use of the term exponential when the increase is the power.
Yeah, that makes sense. I actually, I think I've just, learned something new. I thought exponential was referring to an exponent, like a squared or something like that. I didn't realize that it's 2 to the a.
Right.
Okay.
So that's a good point, and I'm glad to clarify that. In our case here, we have here our rates are r squared, r cubed, r to the fourth, r to the fifth, r to the sixth as we go down, k2, k3, k4, k5, k6. So that really is an exponential series. On the other hand, in our mass action, we have a cubed as the rate, and that in that case, the dependence on a is a power law. And so the standard terminology is a power law versus an exponent. So thank you for asking for the clarification. Any other questions about that?
Question.
Great.
I think I understand with 3, so it says as a function of temperature, and with that, are we considering like temperature in real life where it can like break down reactions, or are we just considering it just as a hypothetical?
Well, the question was one that you can frame the way you like. I think I was thinking about temperature in real life. I mean, if we go to temperature can't go below absolute zero. At absolute zero, we expect chemical reactions to stop. I guess there's still some 0 point energy, but not much. And if we go to high enough temperature, molecules break down, then atoms break down, then if we go to high enough temperature, the protons will break down. If we go to high enough temperature, the quarks will break down. So the questions stop being meaningful. So it's sort of up to you to ask the question, to define what the range of temperatures you're going to consider is. I say, the limit is large temperature. I suppose at high enough temperature, everything ceases to exist. So then the question is sort of meaningless. So it's up to you to make that definition. I'd accept any definition you chose as long as you explained why you made it.
Okay, that makes sense. Those are all my questions. Thank you.
Great. So I hope in that case going over these things was useful. I know, it's always a choice between pushing on with new material and reviewing the material we have, but this course really isn't a prerequisite for anything. And I think it's important that we all learn as much as we can from the things we're doing together. And again, I don't know what people's experience is, but I don't see these concepts necessarily being taught in a lot of classes. I think probably Vikram teaches some of them, probably Paul teaches some of them. But some of these sorts of reasoning questions, I think, are very important if you're an engineer. As a scientist or an engineer, I think they're very important. And developing a sort of a common sense of what makes sense, what's reasonable, is not easy. And as the question about what's a reasonable time scale for what's a reasonable value for K brings up, there are times when we can't answer that question, and there are times when we can, and we have to know when we can and when we can't answer a particular question. Okay, let's get going again, see how far we get. Let's see. Okay, so that was a different cascade. Okay, So just coming back to this comment, which I really made earlier about picking timescales. And this example of the exponentially varying timescales is one where there is no single times for the simulation that will let us see everything. In a sense, what we would like to be able to do is have our time step grow exponentially as the time goes. In some simulation methodologies, we could do that. Mathematica, I'm really going to lose at this point. Tellurium doesn't let us do that. Tellurium is going to confine us to a fixed time interval and a fixed duration of the simulation. And so we're going to have to accept the fact that we can't do everything with a single simulation. We may have to sometimes do multiple simulations to explore what's happening. When they're mixed timescales, we have a problem computationally. And this does happen in biology. And there really is no solution to it. Ultimately, we can get stuck. If we have something that happens very fast and other things that happen very much slower, there's a mathematical methodology called separation of timescales, where you assume that the fast things happen instantaneously, that they're equilibrated over 0 time. And in that case, the fast things are no longer a differential equation. You write them as in the form of functions, which are the solutions to d by dt equals 0 for that thing. And in that case, you can simplify things a lot. And I mentioned action potentials as an example where you have very fast and slow processes happening simultaneously. And when people do things like burst calculations for action potentials, where you have action potentials firing in a burst and turning on and the burst turns off again, you do what's called separation of timescales. You solve the fast process by itself, assuming the slow process is constant in time. And then you find the equilibrated fast process and you then put that into the slow process. And when there only are 2 timescales, one fast and one slow, then you can do that, and you can do that numerically too. You run the simulation for the fast process with short time. Then you separate that out, you get the results in a table, and you put them into the slow process and you do it. And here's an example. Suppose that we have a problem where we have a fast process that takes a second, and we need to subdivide that into 1,000 time steps in order to be able to get it numerically correct. And suppose that there is a slow process that takes a day, and we need to simulate that slow process in units of a minute. So that means that to simulate the fast process by itself, to simulate 1 second, we need 1,000 steps. To simulate the slow process by itself, we need to simulate a day, 1,440 steps. If we want to put the two together, then we have to simulate a day at a scale of a millisecond. That's 9 times 10 to the 7th steps. So that's a lot of time steps. In fact, you'll discover that, and this is something you can try, just be prepared to restart your kernel afterwards. When you do your m.simulate or r.simulate in Tellurium, say simulate from 0 to 100 with 100 steps, commas 100, and then do 1,000, and then do 10,000, and then do 100,000. And initially what will happen is that it will slow down, which is what you'd expect. And at some point, typically around 50,000, it will crash because you'll have a memory allocation problem and you won't be able to do it. And so you have to be aware of that kind of problem. And so if I were going to actually try to simulate 10 to the 7th steps, 9 times 10 to the 7th steps with Tellurium, I could not do that by writing simulate 0 to 1440, comma 9 times 10 to the 7th. If I throw that into simulate, it would crash. I would have to write a loop where I simulate forward a few 10,000 time steps, 10,000 microsteps at a time, and iterate over it. And that has to do with a particular way that Tellurium does simulation time stepping. The way it does it makes it computationally very efficient, but it means when you ask for a lot of steps at once, it uses a lot of memory. If there's a formal separation of timescales, again, with just two steps, as I mentioned, there's this, again, this separation of timescales method that people use. And again, you assume that the slow process is unchanging, acts as a boundary species, and you solve the fast process. And then you assume that the fast process is equilibrated, and then solve the slow process. And again, in situations like action potentials for neurons, that works really well. If you have intermediate timescales, so things are happening at the scale of 1 millisecond, 1 second, 1 hour, 1 day in the same system, you can't do separation of timescales anymore. It really only works if there are 2 or 3 well-separated timescales. If you have a blend of timescales that is continuous, or you have more than 2 or 3 separate timescales, then you're stuck. Fundamentally, the problems become hard. And unfortunately, we find that in real biology, a lot of times the timescales do overlap. And that means that numerically they're quite demanding. There's no workaround. The next exercise that I wanted to do was coming back to parameter scans. And I'm debating but how much of this we want to do actually as an exercise, how much I'll just show you. Quite a few people did these things by themselves. It depends a little bit on how much Python people have used. And there are different ways of doing parameter scans, some of which are more elegant than others. One way to do them is to do what we've been doing so far, which is to run the simulations and use the show equals false in the plot and have the plot itself do the overlaying of the simulation. And that's a reasonable thing to do, provided that we don't want to somehow analyze the data simultaneously. And so one of the things that we can do, and maybe let's not do this as an exercise given the time. We'll come back. There's a different exercise that's based on this that I want to get to that I think is more interesting and more important, because it comes back to something people did have an issue with in the homework. But I just want to walk you through this. Array manipulations in Python are not the most convenient things in the world. There are a lot of very powerful array operations, slicing operators, and as I mentioned, NumPy has some functions that will find the line with the biggest value and return the line number and the value. There are a lot of very powerful array manipulation functions. They tend to be a little bit non-intuitive. And so my guidance on that is if you say, how do I find the line in my array that has the biggest value and the index for it? I would type exactly those words into Google. Python, how do I find the line with the, or actually I'd say NumPy, because it's a NumPy, going to be a NumPy function. NumPy, how do I do this? And it will pull up Stack Overflow with an example of what you need to do. I wouldn't memorize it. I would just, once you have it, create that code snippet somewhere and keep it so you don't have to keep looking it up. But I sure don't remember. For array manipulation, I use a lot NumPy's hstack and vstack commands, and they're pretty clunky. And I'm sure that the Pythonic experts in the room will have more elegant solutions to these problems. But let me just walk you through this example, and we're not going to do it together. And then there's one that I would like to do together because it was a homework problem, and I don't think anybody got the homework problem to work. So here we're going to have our enzymatic reaction. We'll have E plus S goes reversibly to ES complex, and then the complex will decay irreversibly to enzyme plus product. And my suggestion was to do a parameter scan for the rate of production of P. And there are a number of things that we can do. It's sort of a kludge, but I often like to get the time series as a separate line. And when you do r.simulate, the r.simulate object, M, the result, I can do a square bracket time, and that will pull the time column out of it. So I can actually pull out the columns by their names, which is quite convenient, or by their indices. I sometimes forget how to do that, and so I'm going to create a column vector, which is just the times. And so I'll run simulate and ask just for the time. And that will give me a column vector with my time intervals. I'm now going to run this again. And now I'm going to ask for some result. And the one I'm going to ask for here will be the rate at which ES, rate at which I'm producing product, which is, in this case, I called it J3. ES goes to E plus P. The rate is R times ES. I could have just asked for ES because they're proportional to each other. But I'm going to ask for that rate, and that rate law in principle could be something more complicated. By default, if I just do simulate, it will give me the variables, but it won't give me the rates. And so if I want the rates, I must ask for them by name. And so here I'll say n equals r.simulate, 0, 20, 100 time steps, the micro steps. And I'll ask for J3, which is the rate at which ES is converted to product. So I'm going to now get a column, which is the rate of production at each time of my product. And the key thing here is that the column vector J3 will have the same number of rows as the time that I created before. I can now use the np.hstack command to assemble an array where, as I iterate, I can keep adding columns to my array on the right-hand side. And the np.hstack has the form array equals np.hstack, open parenthesis, and then a list of the things that I want to concatenate. And I could, in principle, have more than two. I could say array 1, array 2, array 3, array 4, array 5. It'll glue them all together. The one thing that I have to be careful of is that the number of rows must be equal. If one of my arrays, my column arrays, has a different number of rows from the others, this will crash. And so I couldn't change the time step, the microstep unit, or the length of the simulation without crashing. And so this is a way that I can then successively have one row, the first row, I'm sorry, the first column is the times, and then I add my values for the first parameter, my values for the second parameter, my values for the third parameter, and so on. And so I can write a simple loop here I do a sort of a test simulation, which just gives me my time step. So m equals r dot simulate 0, 20, 100 time. That'll give me 100 rows of different times. And that'll give me my first column. Now I'm going to do S in n numpy a range, 0 to 10, steps of 1. I'm now going to reset my simulation. And now I run the simulation and get the rate of production of product versus time. And so now each column is, the first column will be the rate of production of product when S, my amount of substrate, was 0. The second will be the rate of production of product versus time when the amount of substrate was 1. The third will be the amount of product produced per time versus time when the amount of substrate is 3, so on. Remember that with numpy a range, I stop before the end. So the values of S will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I will never get 10. I'm h-stacking each one. And so at the end of this, I will have 11 columns, the left-hand most one being time, and the successive ones being S equals 1, 0, S equals 1, S equals 2, and so on. I can use the labeling function to add the values of S, and those are just in order for the columns, excluding the first column. So if I do label.append, I'm stacking S equals 0, S equals 1, S equals 2, and so on. And if I then do a plot array with my labels, I'll get that. And I showed this to you a little bit before. A lot of people came up with this in the homework on their own. Some people came up with slightly more elegant ways of doing it. But this example is available, and this is code that I use a lot. It's not the most elegant code in the world, but it's something that I think is useful. If people have not seen hstack and want to go over this, the slides will be here. I do encourage you to do this exercise on your own. It was in the homework, but if you had trouble with it, I encourage you to go back. And you can look at the example here for a source. But the thing that I did want to do, which was maybe more important, because people were having some trouble getting this to work, was plotting something that we need to do a lot, which is plotting steady states as a function of parameters. And so now let's come back, and this time I do want people to do this. I want people to fire up their Tellurium. You've got it running from the example we did before. And I want to write this enzymatic reaction. And I'd like people to write this enzymatic reaction out. And I'm going to use the amount of substrate as a boundary species. So we're going to put that $sign in front of it, which means that it's not used up. And one of the things that people noticed when they plotted the results of this by itself is that the amount of product being produced increases continually in time. So you have everything else go up and then either stay steady or come down, but the amount of product kept going up. And you had a problem when that happened, just the way in the example we did a few minutes ago, the time scales were inconsistent. We couldn't see what was happening for the slow reactions on the same time scale that we could see for the fast reaction. If most of our species come up and have a maximum, and one species concentration is increasing continually in time, then when we plot, we'll just see the one increasing continually in time, and that will, the scale will get compressed, for the others, and we won't be able to see what's going on. And so one way to deal with that would be to have a logarithmic times the y scale. Then we have to worry that we can't do logarithm of 0, so we have to have a cutoff for small values. That works. The other way to do it is to suppress the display of the value that's increasing in time. And so to use column selection to not display the ones that are causing the problem. Another way to do it, which is a bit of a cheat, is that the rate of production of product, E plus P, the amount of P, the P isn't used for anything. And if I put a $ in front of P, effectively what that's saying is P is being taken out of my system. And that will keep the value of P from going to infinity without affecting everything else. If P were used in anything else, it wouldn't work. Or if I had a reversible reaction, it wouldn't work. But you can $ P, and that will prevent you from getting that runaway that is an issue. So I'd like people to implement this little enzymatic reaction and raise your hand when you've got that working.
Are we plotting the reactions or just the species?
For the moment, I haven't told you what to plot. You could just do a plot of the whole thing for the moment, if you want, just to get a sense of what's going on. Or you could use the column selection and plot the rates too. Okay. Does anybody need more time? It looks like people are doing pretty well. Does anybody need, if you need more time, now raise your, now speak up if you need more time. Everybody okay? Okay. So I'm going to show you another simple Python method. Again, not a very elegant one, but it's how I've always done it. And if people have better ways, I'm sure there are. You can do that. If I want to plot a parameter value versus an equilibrium value, I tend to build those arrays using a VStack. So HStack plunks arrays together horizontally, adds columns. VStack adds rows to arrays. And the one thing that you have to do with HStack, we created that column, which was the times for our left-hand most placeholder. For VStack, we don't have anything obvious to put at the top. And so we have to create an empty array. And NumPy has a particularly awkward way of doing that, which is array equals np.empty parenthesis shape equals, and then the number of rows, comma, the number of columns. And the trick with these is always remembering, is it regular parentheses or is it a list with square brackets? Sometimes you think it's going to be regular parentheses and it's a list. And so if I want to create an empty, it's not a row, a placeholder, a container with 2 columns in it and no rows, I use np.empty shape equals 0, 2. And again, you can do this in other ways, and people may have a more elegant way of doing it. But that's how I've always done it. If somebody has better code that you want me to distribute, I'd be delighted. And that one, again, is one of these things that you have to remember. And then I can add rows to my existing array using np.vstack. And here again, it's square brackets. You might expect it to be something else. And it's a square bracket. It's containing the list. And the first element of the list is the thing that you're attaching to. And the second element is the row to append. And what's confusing is that the row to append goes in square bracket. And so if I'm going to be appending the parameter value and the result, it's results, comma, square bracket, parameter value, comma, value. And so in this case, if I've calculated for each value of S that I've got, I want to know what my value of J3 was, my rate was. I'm going to put that together. And so now give that a shot. Why don't you try to do that? So you've got your simulation. I want you to write a little loop where you change the value of S. Remember that you're going to have to reset the simulation each time. Run the simulation to long enough that you get an equilibrated result. Output the value of J3, and then stack S comma equilibrium value of J3. And if people need to, I don't have, let's see if I have it here. Since we don't have a lot of time, I'll show you how I did it, because otherwise remembering that np.empty is a little bit awkward. But why don't people try this? So take the code you've written to define the simulation. That R dot conserved moiety analysis shouldn't be needed anymore. The R dot get steady state values, I asked you to use that in the homework. And somewhat to my surprise, it worked in that homework problem. I will warn you that pretty often that get steady state values fails. And if it does, just run the simulation for a long time and use the value at the end of the simulation. You shouldn't need the conserved moiety analysis anymore. That's an old myth. So take the code that you just wrote that defines this enzymatic reaction, and now you're going to be calculating what is the rate of production of product at long time as a function of the concentration of substrate. Now give people a minute to type that in and try it out. And again, if you're a Python expert and you have more elegant ways of doing the same thing, please feel free to use them. And please use the chat to share them and send me a copy by email, and I'll distribute it that way to class too. Because I certainly don't believe that this particular way of doing parameter scans is the most elegant. I tend to be a big believer in not reinventing things. So once I have a method that works, I tend to stick with it. That doesn't mean that it's the prettiest way of doing it. And the reason I wanted to spend some time on this was because, yes, Joel says if it works, don't change it. Yeah, well, in my case, that's how I've lived with this. Although occasionally I'll have something very inelegant, like iterating through an array to find the largest value when there's a numpy function that will return it to you immediately. And so I'm quite happy to have students come to me and say, there's some basic Python that you're missing here. I'm always happy to learn. Not always happy to have to redo my slide decks, but that's a different. But I asked people to do this in the context of homework 3. And I know in homework 3, there was some ambiguity about what large and small values of K were. But I don't think anybody got the parameter dependence on the I to work. I don't think anybody got it to work, maybe one person. And so I wanted to make sure that computationally, everybody was able to do this so that we made sure, because this is something we'll need to do a lot. This is basically, people who've been taking Randy Beer's course, if you're going to do bifurcation analysis, this is the slightly clunky way that you would do bifurcation analysis in Tellurium. Because you'd be changing S continuously and you'd be looking for a discontinuous change in J3. And that would be a bifurcation. And Connor, I know in your homework you had a plot function that did some very nice streamline displaying, which would be nice to show everybody, because that was not a function I was familiar with.
Okay, if you want, I can send code that runs that into the chat.
Maybe, I don't know for today, but maybe next week, if you have time, you could make a slide or two and show people how to do that. We could email that around, because I thought
Sure.
that was.
Are you talking about the surface plot that had the parameter scanned and then had like the time series as basically like a sheet folded above it?
So you had two things in your homework. One of them was you did a nice 3D plot.
Yeah.
Time versus parameter value, not just the final value. But then you also had a phase portrait where you showed how you had for each value of S, you had how X versus Y changed, and so it was a streamline plot. And that was a function in the plot library that I wasn't familiar with.
So that one, I think I said this in my homework. For that specific plot, I stepped outside of Tellurium to make it. I used a Python function. I feel like I remember from the book that we're using, there is a case where he makes a phase portrait with Tellurium, but it's a lot. Towards the end of the book, there's 2 points where he has flows that he lists. One he uses Tellurium for, but I think the code was a lot more complex, and then he switched to
the one place he uses XPP auth for those.
Okay.
He uses Bart Ehrmantraut's tool XPP auth. It's the only place he switches out of Tellurium in the book.
Okay.
But in your case, I understand that you went outside of Tellurium, but you could still use Tellurium and then use VStack. HStack to build the horizontal to put your columns together and then pass it to that plotting function. So you could run the individual simulations to get the time series and then assemble them into an array that was plotted using your function.
Yeah, I'll show. I can send you the code after class to show you how I did it.
Well, we can talk about that separately, but plotting plotting those phase portraits is nice, and we can do it here, but you don't get the vectors on. That was what I thought was really cool. Okay. Anyway, let's get everybody through this one. And again, if people have better ways of doing it, I'm happy to for next year. I'm happy to first just share them with the class for this year, and then update the slides for next year. So there's a more Pythonic way of doing it. So raise your hand when you've got this working. All right, and if it doesn't work, speak up, and we'll try to help debug. As I say, that conserved moiety analysis equals true shouldn't be necessary. Get steady state value should work. If it doesn't, just do a r.simulate for a long time, and that'll give you the same result. Take a little slow, be run a little slow. And if you've got it working and you're waiting for your classmates, you could try doing it with a different parameter. For example, you could scan the amount of enzyme instead of the amount of substrate. Or you could try changing one of the K values and doing the same thing.
I'm a little unsure as to what the plot is actually showing us, though. Will you go over it after everyone's done?
Exactly. That's my goal is to do that. Exactly.
Okay.
But I want to make sure everybody has the plot before I start talking. Again, the principle of operation here is that we create an empty space to put our array. We iterate over the parameter. We have to remember to do a reset. Some people in Herbert's problem did a reset, and some people didn't. And actually, when I was grading them initially, I thought, well, Herbert expected you to do a reset, but actually not doing the reset gave you a more interesting result because you could see how the system's equilibrium changed when you made the parameter change. So actually, I decided that I liked not doing the reset. Since you really need to do both, one with the reset, one without. In this case, you need to do the reset. If you don't do the reset, it'll wrong. And in principle, you might be able to do an append rather than a vstack, but then you have to do then you have to convert your list into a NumPy array. So one way or the other, you pay. Again, when you're ready, raise your hand and I'll go forward. Okay, looks like most people are ready. Is there anybody who needs more time? Everybody got it? Don't be shy when I say it. That's a genuine question. When I say, do you need more time? Don't be shy about saying yes. If you need more time, other people almost certainly need more time. Okay, so let's see what our result looked like. I realized in the homework that I gave you, I gave the plot, but somehow the axis labels got lost for the plot when I pasted it in. And there was a specific question in the homework, which was as a function of I, in that case, was the curve concave or convex? And this is the example. So did people get something that looked like this? How many people got something that looked more or less like this? 1, 2, 3. Did people get something that looked different? 4. How many people got nothing? I'm a little nervous by the silence. What happened to you? Worked great. Okay. So what's interesting here is we're plotting the rate of production of P as a function of the amount of substrate. And if we imagined that our reaction were just substrate goes to product by itself with no enzyme, in that case, our rate law with mass action would be that the rate would be proportional to the amount of substrate. So our rate would be K times the amount of substrate. In other words, we would expect to see a straight line, a linear increase, where the slope was that value of K. Instead, what we see is something else. At 0, the value is 0. the rate of production of product with no substrate has to be 0. If there's no substrate, we can't turn it into products. It better be 0 at 0. We see that for small values of substrate, for small concentrations of substrate, the rate of production of product increases, and that rate of increase is maximal. And this is, again, thinking about how do we describe what we see? Well, there are not that many features in this curve. In the first place, we could say this curve is convex. It's above linear. It also is monotonically increasing. The value increases continuously as I go to the right. Its slope is maximal at 0. And its slope decreases continuously as I go to the right. I can't say for certain, looking at this curve, whether if I took S to infinity, whether it would reach a finite value or whether it would keep going up slower and slower, but go to infinity. Can't tell that from this curve. If I made S go up to 1,000, then maybe I could tell that. Somebody could try that. Why doesn't somebody increase the loop in my, for S in NumPy A range, instead of going from 0.1 to 10, go from 0.1 to 100, and to keep things in a reasonable amount of time, make the step size 1. Tell me what you see. Does it separate? Does dp dt continue to increase, or does it reach a maximum value?
No, it reaches a maximum value, close to 1, closer and closer to 1.
So it saturates at 1. So in fact, my choice of that range of S wasn't sufficient to answer that question. So this is an example of my not observing what I suggested, which is to change the value of the x-axis to make sure you answer your question. Good point. So the answer here, which is what is interesting, is that this shape of this curve is the Michaelis-Menten rate law. The temporal behavior of the system for E goes to P is different if I include the substrate reaction. But if I only care about the long time rate of production of P, then I could write a reaction which is E goes to P with a rate that has this particular functional form as a function of S. And I said E goes to P, S goes to P with a rate with a particular functional form of S. Okay, does that make sense for people? And so the last thing that I would like people to do is to do homework problem 5.3.1. And what I want you to do here is add one reversible reaction. And that reversible reaction now is ES here goes to ESI at a rate K, and you'll just set that rate to 1 again. Or you can use R if you like. R times ES times I. And ESI goes back to ES at a rate R times ESI. And then what I'd like you to do is, instead of scanning for S, pick a value of S, pick a value of S like 5 or 10, and now scan I and see what happens. And in this case, what you should find is that the amount of inhibitor, as the amount of inhibitor goes up, the rate of reaction goes down. And in this case, it should be concave below the linear function. And this is actually what's called a decreasing Michaelis function. As it happens. And we can see that in this case, if we had I go to infinity, we asked the question about inhibitors. Does it shut the reaction off completely if you have a lot? In this case, you can see that if you made the amount of inhibitor go to infinity, the rate of reaction would go to 0. And what's going to matter here is going to be, we're going to set all the rate constants to 1, so we're not going to worry about the rate constant part of it. But what's going to matter here is whether the amount of inhibitor is a lot compared to the amount of enzyme or not. And so why don't people try this out? See what you get. So you don't have to change anything that you did before, except that instead of scanning S, you're going to scan I in your outside loop outside. And you're going to add 2 lines to your existing simulation, which is ES plus I goes to ESI, and ESI goes to ES.
You should probably also make I constant, right?
You're going to have
Putting
to
a
put a
dollar
dollar
sign.
sign. You have to put a dollar sign on your I. Yes. People need me to go back to the previous slide. I can, but I think you should have all the code you need. It's adding 2 lines to your code for that additional side branch reaction, and then changing the scan from being over S to being over I. And this is, I think, a good exercise of generalizing your code. You wrote a parameter scan that gives you the equilibrium values as a function of parameter. Now you're changing the parameter that you're scanning. If people have any questions or problems, please ask. And if you get it quickly, then there's a lot you can explore. You can change the rate constants. You could change the amount of E as well as of I. You could change the amount of S as well as so on. Lindsay, you've already got it. That was quick. Did you get something that looked like my curve or something else?
Yeah, decaying to 0.
Sean says, can somebody share some code? Lindsay, do you want to try, or do you want to screen share it and show us your code?
Yeah, sure, I can.
Okay, let me do that. Go ahead, you should be able to.
Okay, so this first one, I did another parameter E, but this is the one that I got for I.
Okay, that looks great. And let's look at the code together, and maybe Sean can take a look at how you did it.
The get steady state values didn't work for me, so I just had to simulate for a long time and take the end.
Yeah, that get steady state value is finicky. If the matrix it uses a matrix inversion to calculate the final value, and if there are singularities in the matrix, it will fail. And so that conserved moieties flag is supposed to check for matrix and singularities, but it doesn't always work. So I tend not to use it. Herbert likes it because he worked hard to make it work. And so and let's look at your model definition too while you got it there, just so we can see how you added that side branch to the where you. Okay, there you go. Good. So yeah, so it's R4 and R5, right? Yeah. Let's stick with them out. There we go. Perfect. Yeah. So you added a line ES plus $I goes to ESI. That's the sequestration of ES by the inhibitor. And then ESI reversibly goes back to ES plus I, and the rates are both mass action. So let's leave that up to make sure everybody has that.
One thing that is interesting is that since I is constant, it's basically the same as the rate of KFI. Right? That's actually the control, right? In this situation
Yep.
here.
No. Yeah, so you could definitely ask the question, which things are the most important? Or if I have a lot of substrate, let's make substrate equal to 10 in your equation, Lindsay. You make S equal to 10, and now run it again and see what happens. Doesn't do it. Doesn't change. It makes it steeper, right? It shuts down faster in this case. So one could in principle scan multiple parameters simultaneously and put them on the same plot, or do 3D plots the way Connor was doing it. The Matplotlib has all sorts of fancy plotting features. Remembering how to call them isn't always so easy though, so I tend to stick with the simpler ones, but that's great. Let's put the amount of S back to 1, and let's make the amount of enzyme 10. So that one doesn't change very much.
Yeah, it's hard to tell without the exact values, but
It changed the scale. It's 3.0.
Yes.
It was 0.3.
No. So again, one could in principle do multiple scans of this kind. You could put this loop inside of another loop, overlay the plots, and see how things depended on 2 parameters simultaneously. Okay. Did everybody get this base simulation to work now? Anybody still having trouble with that? The other thing that we could do with this is this was one of the 2 problems. In this case, the inhibitor bound to the complex, to ES. The other one would be, and actually, Lindsay, if you come back, let's do the other one. It only takes 1 second to do it, and that'll be the last thing we'll do. You can screen share again. I hope that this was a bit of an experiment. You know, previously I've typed and shown things, but I think watching me type isn't very interesting. I think it's better if we can, at least some of the time, have you guys do it. Or if we go back to your model definition at the top, and now instead of saying R4 ES plus I goes to ESI, we get rid of the S. We make it E plus I goes to EI. And then this backward one. So EI goes to E. There we go. That was the first. Remember, I had 2 problems, one of which the inhibitor acted on the enzyme by itself directly, and one acted on the complex. Let's run that one and see what happens.
I think it looks similar.
It looks pretty similar. If we played around with it, we'd find that the dependence on S and E was a little bit different.
It is on the product. It's on the product.
Yeah. But those were those homework problems that last week. Those 2 ones where I had that ambiguous question about the rates. I had the problem statement was fine, but then I said, what happens if E is bigger than and less than? And then I said, what happens if the rate constants are bigger or less than? And the way I explained the rate constants didn't make sense if you hadn't actually written the rates out. But this was the last part of that problem. It said, how does it depend on the concentration? And I think that this is, so we didn't get to the calculation of the Michaelis-Menten relation analytically now, but we've done it computationally. We've seen Michaelis rates. And now we'll use this next time, we'll come back and we'll use this observation of enzymatic behavior to motivate a simple computation of the Michaelis constant, Michaelis rate law. And then we'll go one step further and ask the question if we had cooperative effects. For example, if we had to bind 2 of the enzyme, or if the rate took 2 steps rather than 1 step, then we'll get what's called a Hill function. And we'll do that together next time. Are there any questions before we break today? Please, go ahead. So, sorry, say that again? And that's a good question. Joel, do you have any, send me an email and I will send you a bunch of links to previous student projects. How's that? Okay, a very good question. The question was, can we see some previous NanoHub projects to see what they look like?
Hmm.
And one of the problems in NanoHub is that the searching is not very good. And so it would be, I need to give you the links and I need to dig those out. I don't have them on the top of my head. A lot of them are going to be about disease because last 2 years, the course was taught around modeling infectious diseases. They're going to be those, but there was a nice project by Jeffrey Coulter on coupled neuronal oscillators and spiking. And I know one person was interested in working in that general area this year. And there were definitely some cancer simulations last year and the year before. So I can share you a couple of examples to give you an idea of what's possible and what's and some of them will be one and maybe I'll be silent about my opinion about how effective these are as communication. They were all great projects. Some of them I think were more effective than others in terms of their ability to have a user learn from it. And so I think the best way to make the decision about that is to try it yourself and see what happens. So I'll try to give you, remind me. Joel, you could, since we talk frequently, Joel, you can nag me about that. Make sure that by the end of the week, I send out a series of links with some NanoHub examples. Okay. Any other comments or questions? That was a good point. I appreciate that. Okay, well then, thank you. Sorry, go ahead.
So I just wanted to say real quick, I presented my project idea last week, and since then I've talked with Lindsay, and since our project ideas were kind of similar, I think I want to work with her on her project idea instead. Is that
That's
okay?
These are very fluid. The reason I wanted people to start early was to have exactly that kind of thing. Groups can form, fission, people could change their minds. By all means, if you could come up with a joint project that you believe in, these projects are a lot of work. And so, as I say, I don't tell people they can't work on their own. But in my experience, it's enough work that you benefit by working as a team.
Mm-hmm. And so should we just like, if there's any other submissions along the line for the project, should we basically submit the same document to each of our canvases?
Yeah. Yes.
Okay.
Or submit. You could either do it that way. That came up with the pre-proposals because there were some teams, and some people submitted a pre-proposal and each person put in the same thing, which is fine. Otherwise, if one of you submits it and the other one just reminds me, by the way, I submitted so-and-so submitted it on my behalf, then I'll put the grade in for you as well.
Okay.
The one place it'll be different is I mean, usually the grades wind up being the same. But when you do your final presentations, your oral presentations will be you'll submit one progress project report, you'll upload one file. But when you do the verbal presentation, you'll have to divvy up the project. You'll both speak when you present it. And you, of course, you'll be graded separately for your oral presentation. It's unusual that one person does a wonderful job on the oral presentation, the other person stumbles, but occasionally that can happen. One person has been in Toastmasters and the other person is just beginning to learn English. And so, of course, I won't take off because somebody's English isn't perfect, but I mean something somewhat different, which is sometimes the oral presentations are not exactly the same. So those would be graded by what you did. But otherwise, if it's a joint project, everything is jointly graded.
Okay, thank you. That's the only thing I had to ask.
Okay, great. Okay, anything else? Okay, well, thank you again. I appreciate everybody showing up always. And I will look forward to I would like to try to meet with people virtually in the next few days, at least before next Tuesday. I'd like to try to talk to as many groups as possible about projects. If you're not ready, I understand, but even if it's just half an hour just to go over the slide, your source material, what I really want to look for is to make sure that in your source material there isn't anything that's a mine, so that you can't do this with what we're doing. Because if we're gonna have to make changes, it's fine to make changes now. 3 weeks from now, it's getting late to change the topic. And so if there's going to be a problem, I want to find it as soon as possible. That's really the main reason to meet and go over the source material. Okay. Okay, thanks everybody. See you.